Now let's go over the second derivative test for relative extrema. Like the first derivative test, the second derivative test is used to identify relative extrema as maxima or minima. To understand how the second derivative test works, let's consider the graph of the two functions down here. Now in the first graph, we're assuming that our second derivative at c is greater than 0, which means that our graph is concave upward near c f of c. Well, if that's the case, then obviously we're going to have a relative minimum at c f of c. On the other hand, if we assume that our second derivative is negative, then our graph has to be concave downward near c f of c, which implies that we have to have a relative maximum. So this gives us a way of determining whether an extrema that we've found is a maximum or minimum. That is, we can take the second derivative and evaluate it. If our second derivative is positive, we're going to have a relative minimum. If our second derivative is negative, we're going to have a relative maximum. And that's how the second derivative test works. So let's look at a statement of the second derivative test. So here's the formal statement for the second derivative test. We let f of x be a function in which the first derivative is 0, and the second derivative exists in an open interval about the point c in question. Then, if the second derivative is greater than 0, then f has a relative minimum at c f of c. And once again, that's because if the second derivative is greater than 0, your function is going to be concave upward, and so you're going to have a minimum at that point, at c, x equaling c. On the other hand, if your second derivative is negative, then your function has a relative maximum at c f of c. And that's because if your second derivative is negative, then your function is concave downward, and so you're going to have a maximum. On the other hand, if your second derivative is equal to 0, then the test fails and you have to go back and use the first derivative test. Let's take a look at an example of how we use this test. Now here we're given the function 3x to the 5th minus 5x cubed, and we want to use the second derivative test to identify relative extrema. So the first thing we need to do is we need to find where we have potential relative extrema. So that means we want to find where the first derivative is equal to 0 or does not exist. So taking the derivative of this function, we get now we're not going to have to worry about where it does not exist because obviously this is a polynomial, it exists everywhere. So setting it equal to 0 and factoring this, we're going to get and setting each individual term equal to 0, we obviously get x equals 0 for this one and x equals plus and minus 1. So that's where we have potential relative extrema. So x equals 0 and plus and minus 1. Now we have to test these to determine which are relative max and which are relative min. So if we start out with -1, now we're going to use the second derivative test, so we need to take the second derivative of our function. So let's put that over here. Let's note that f double prime. So that's going to be 60 x cubed minus 30x, just 30x. So we take -1, put it in here for x, and let's see what we get back. So let's note that f double prime. So putting negative 1 in here, negative 1 cubed is negative, so we're going to get negative 60 minus 30 times negative 1, that's going to be negative 30, so plus 30. And we get back negative 30, which is less than 0. So our graph is concave down at x equaling negative 1, and so therefore this is a relative maximum. So negative 1, f of negative 1, and let's see, putting negative 1 up here, we're going to get negative 3 minus negative 5, so that's going to be 2. So this is a relative max. Now let's look at x equaling 1. So if we take the second derivative, evaluate it at 1. So putting 1 in here for x, here and here, we're going to get 60 minus 30, which is positive 30, greater than 0. That means our graph is concave upward at 1. So that means that we have a relative minimum when x is equal to 1. So 1, f of 1, and putting 1 in here for x, we're going to get 3 minus 5, negative 2. That is going to be a relative minimum. Now what if x is equal to 0? Well, if x equals 0, taking the second derivative and putting 0 in here for x, we get that, well, we get back 0. So that means that the test fails. We have no idea whether 0 is going to be where we have a relative max or a minimum. So the test fails. And we need to go back to the first derivative test. So over here, let's just do our first derivative test. So we have to mark off our critical numbers 0, 1, negative 1, and then pick test values around 0 to see if we have a change in the sign of the first derivative. Remember, what we're looking for here is the sign of f prime. That's how the first derivative test works. So we'll pick test numbers like negative 1/2, positive 1/2, put these numbers back into the first derivative right here, and then see if we get back positive or negative numbers. So f double prime, remember f double prime, that's going to be our 15x to the 4th. And if we evaluate f prime of negative 1/2, putting negative 1/2 in here for x, you can evaluate that on your calculator. You're going to get back negative 2.8125. So our first derivative is negative to the left of 0. If you put positive 1/2 in for f prime, you're going to get back the same number. And so our first derivative to the right of 0 is negative as well. So what that means is that 0 is neither a relative maximum nor a relative minimum. So we'll put it over here. 0, f of 0 is 0, is neither a relative max nor minimum. And now let's take a look at the graph of the function and see if that agrees with what we found here. Remember, we found that we have a relative maximum at -1, 2, a relative minimum at 1, -2, and 0, 0 is neither a relative max nor a relative minimum. So let's take a look at the graph. So right here's the graph of our function. We see that right here at -1, 2, we do have a relative maximum. Right here at 1, -2, we do have a relative minimum. And right here at the origin, 0, 0, yes, we have neither a relative max nor a relative minimum. Our function is decreasing, flattens out, and then it continues to decrease, so you have neither a relative maximum nor a relative minimum. So that's an example of how we use the second derivative test. Let's take a look at an example that illustrates why the test fails when the second derivative is equal to 0. For this example, we're going to consider two functions, f of x equals x to the fourth and negative x to the fourth power. Now you notice for x to the fourth, our graph is going to be concave up, and we have a minimum, a relative minimum. It's actually an absolute minimum at 0, 0. You can see that from the graph. So 0, 0, and you can verify this using the first derivative test. 0, 0 is a relative minimum. Now, if we were to try to apply the second derivative test at x equaling 0, notice what we would get. We would get our first derivative. Notice that that is, first of all, 4x cubed. Our second derivative is 12x squared. And if we evaluate the second derivative at 0, of course we get back 0, putting 0 in for x. So this function has a relative minimum at 0, 0, and its second derivative at 0 is 0. Now if we simply change this function by putting a negative there, so now we're considering the function negative x to the fourth, notice that 0, 0 down here, this is a relative maximum now. It's actually an absolute maximum, but it is a relative maximum. And if we try to apply the second derivative test here, notice what we get. Our first derivative is negative 4x cubed. Second derivative. And so if we take the second derivative at 0, notice we get back 0. So you see, this is why the test fails. Here is an example where we have a relative minimum at x equaling 0, and our second derivative came out to be 0. Here we have another function where we have a relative maximum when x is equal to 0, and our second derivative also came out to be 0. So when the second derivative comes out to be 0, you have no idea whether you're going to have a relative minimum or a relative maximum, because here are two examples where either one happens with when our second derivative is equaling 0. So that's why the test fails when the second derivative is equal to 0 and you have to go back to the first derivative test. Notice that both of these examples, if you apply the first derivative test will work, because the first derivative test will tell you for this function that you are decreasing and then increasing, and you'll be able to identify that as a minimum. If you apply the first derivative test down here, it will tell you that you are increasing and then decreasing, and you will be able to identify that as a relative maximum. So the first derivative test always works. And that concludes our discussion of the second derivative test.